Hi, everybody. We're going to look at Far-UV air disinfection performance standards. Obviously, all of the existing UVC performance standards apply equally well to any wavelength, including Far-UV. The first standard we want to look at is ASHRAE 241P. This new standard opens the door to using equivalent air changes to select or size equipment for buildings. The target of 4 to 6 ACH is a solid target to aim for. We can engineer any system to deliver that level of performance. Now, when we happened to be with some mechanical contractors when ASHRAE 241P came out, and they started cheering and celebrating all night. But we think they celebrated too soon because we're not sure that buildings can really afford to go to 6 air changes of outside air. It's in summer and winter, that's just impossible. Changing out your fans and motors to 6 air changes per hour from what might be 1 or 2 is not an economically viable alternative. We think that probably we'll get 2 ACH from putting filters and UV in ducts, and buildings will have to make up the other 4 using equivalent air changes from other systems like upper room or portable units or whatever other systems are available out there. So ASHRAE allows us to use equivalent air changes or equivalent Cotter in their term, but you divide by the volume and you get an EAC in terms of outside air change rate. All performance tests measure either airflow and efficiency and some other factors. And those are the primary parameters we need to interpret an EAC. With the EAC, we can do performance comparisons, and this would be in terms of watts per EAC or possibly disinfection efficiency. Economic evaluations can be computed with dollars per EAC. This might become a common term. And then there is quantitative risk assessment. I'm not going to get into QRA, but perhaps the parameter of interest would be risk versus ACH or risk versus EAC. Performance standards can be used to determine the equivalent air change. There are 2 types of performance standards, or actually 3 types of tests. One is an in-duct test where we measure the in-duct efficiency. And then there are in-room performance standards using a model room, which are usually run under steady state conditions. And then there is a transient decay test, in which case a system in a model room is brought down to steady state conditions. In-duct performance standards, we have a number of these. We have standards from EPA for measuring in-duct performance, measuring the removal efficiency across from the inlet to the outlet and the airflow. We have ASHRAE standards, IEC, and ISO standards. These are pretty cut and dry, but they will only apply to in-duct systems. And if we had a Far-UV in-duct system, it would apply. For in-duct performance test data, it's very simple to compute the equivalent air change rate. The EAC, as defined by ASHRAE, is the efficiency times the airflow. For a UV in-duct system, it is the efficiency, which is 1 minus E to the minus K dose, times the airflow divided by the volume. This is cut and dry. This is fundamental. And in terms of interpreting test data, we can still fit a curve. And I've got a number of examples of in-duct performance here. Now, in-room UV performance standards. We have AHAM for testing consumer products. We have ASTM and also the new ASHRAE standard for measuring in-room performance of any type of system. We don't have a real transient reduction test, although the previous tests can be used in that fashion. But many of we don't have a formal standard for it. But without a steady state concentration, some of the tests we're seeing, they go to 0, and that doesn't compute. So we need it to go to steady state concentration, and we need to corroborate the EAC from this type of standard result. Now, what we have is the completely mixed outside air models, the ancient model for performance of an outside air system. We have the equations that are well known, over 100 years old almost. We can compute the steady state concentrations. We compute the removal rate per minute. And this type of test is performed in a model room with a constant source. And the air change rate in the room is the airflow over the volume. Now, from transient decay test data, it's very easy to compute the equivalent air change, thanks to NIOSH, gave us this table in 1994. You see the air changes per hour, and you see the disinfection efficiency at 3 time points, 90, 99, and 99.9. 3 points defines a curve. The decay rate from any concentration indoors is always going to be an exponential decaying curve. And as long as 3 points can be identified on that curve of performance test results, we can match that to the NIOSH 1994 performance measurements. We can determine the time if we don't have a 90 or 99% time, we can use different time values. Now, we have examined all the published EAC values. Many of you have seen these. Some of them are very high, dubiously high. We have checked them against the NIOSH 1994 table, and we have not found a single published EAC which matches or can be corroborated by the NIOSH table. All the published numbers are way too high. Now, if we have steady state test data, it's fairly direct computation to get the EAC, as long as we do have 3 data points. Now, this is a chart produced by CDC and NIOSH about 2009. And this gives us our ACH in terms of removal efficiency at 1 hour. That's 1 time point that we can use to corroborate our equivalent air change value. Since we need 3 points to curve fit the data to the outside air model, we need to get those 3 points from the performance test. They don't always provide that, but if they provide a performance curve, a decay curve, it's easy to determine that, and I will show you how to do that. The completely mixed outside air model expanded from the NIOSH table. We can produce room removal rate per minute as a parameter to check our EAC. We can produce a steady state concentration as a fraction of the total steady state as a point to corroborate our EAC. And we can also look at those previous time values. Now, there are 4 types of air cleaning systems that we know of. There's In-Duct UV and portable UV systems, and these 2 types of systems are virtually identical. Then there is upper room UV and whole room UV systems. We can compute the EAC directly by the basically by the ASHRAE 241 method. The EAC for in-duct systems is simply the efficiency times the air change rate. It's the same for a portable unit. The EAC, now these are fundamental relationships. We have no fundamental relationships for upper rooms or whole room systems. Nobody has developed any yet. We're looking at it. In-duct systems, in-duct and portable UV systems are identical. They're indistinguishable. They perform similarly. Of course, you might say that the performance of a portable unit depends on its location in the room, and that's true. But the in-duct UV system has inlets and outlets, supply and exhaust registers, and the location of those also impacts performance. In room UV systems, we have upper room UV systems and whole room UV systems. And from a performance evaluation point of view, we don't see any difference between these systems. There's an airflow through the room and efficiency of volume. We know the air change rate in the room. We do not know any fundamental relationship for computing the EAC, but we can determine it from test results. Now, is a room a duct? Riley and Wells proposed that we could model a room as a duct. So the question is, if it looks like a duct and it acts like a duct, then in all probability it's a duct, right? Not necessarily. A duct has a velocity profile. The room does not have a velocity profile. The duct is a contained field. The room has air currents of uncertain action and origin. It has an air change rate through the room. We do know that if you pump enough ACH through your room, up around 100 ACH or even 1,000 ACH, the room will act like a duct because it's now got streamlines. But the room itself has air currents made of advection, convection, and diffusion and turbulence. And those aren't easily quantified, and therefore we can't accurately predict at the moment the performance of upper room or in-room systems. We can look at ranges of performance, and I will show you some ranges of performance where you will see what's happening. But let's go back to the very first test, Wells 1938. This was a very innovative piece of work for the time, way ahead of its time. He developed a test, an in-room test for evaluating the decay of E. coli under transient conditions. Fortunately, it did not go to zero, so we can compute this. They removed 57% removal in 17 minutes, which looks superior to an outside air system operating at 1 ACH, which only removes about 63% after 1 hour. Fortunately, we have more than 3 data points. We had 4 data points. We were able to fit a curve. The dotted line is the curve based on NIOSH's model, the outside air model. The data points are Wells's data. Based on this, we compute an outside air equivalent air change rate of 2.2 ACH. Now, Wells used an odd method, which has been carried through the literature, of ratioing slopes, and he came up with a value of 116 equivalent air changes per hour. I said 2.2, I mean 1.67 was the final number. Now, that's about 100 times larger than the value we determined from corroborating his data against the outside air model from NIOSH. However, 1.67 ACH coming from a system that is operating at 0 airflow is a remarkable result. We're getting more equivalent air changes out of this system than there is airflow in the system. And we see this phenomenon occurring with most upper room systems. And we're going to look at some more data here. We took all the data that had enough data to plot points, and we compared them against the NIOSH outside air model, and it looks like this. Here's data from Riley, 1976. We had a number of data points. They fit very well at 10.5 ACH, equivalent air changes per hour. This is much lower than the published values. All these values I'm showing you are much lower. We have Riley 76, BCG. You see the data fits very nicely to 15.4 air changes per hour. We consider that the EAC. And in the next study, Miller 2000, we didn't have a lot of data points, but it appears to fit very well at 5.5 EAC. And in the 2002 test down here, they got very high disinfection rate. It did not actually go to 0. So we were able to estimate this as 20 ACH corroborated against the NIOSH outside air model. We have transient decay performance tests here from various studies. And again, in every case, we come up with a corroborated value, except in certain cases, we're still looking at this data set that are corroborated against the NIOSH model. Here's Dr. Edie's data. We looked at this and we found it performed at a value of 15.2 EAC. This is actually remarkable because of all the corroborated data sets that we have. This Far-UV system outperformed them all at 15 ACH. We have summarized all of the upper room data and plotted it on curves, and we can see that the disinfection efficiency drops with increasing ACH. As the ACH increases, the room begins to act more like a duct. And the model, however, the performance is still higher than what we would predict with a duct. There's something else going on here, and it's happening at low airflows. Now, we normalized all the data to ASHRAE in this case, and we see the data compressed. I'll show you a better version of this. This is the final summary. The red bars indicate the EAC results. Not all of these are corroborated, but you can see variation. We normalized all the EACs in the literature to Bacillus atrophaeus, since it had the lowest resistance or the highest resistance. And you can see that in the blue, they all get compressed together. There's a few high points here that we are suspect. They don't have enough data sets, enough data points. But the overall average for in-room systems was about 3.5 ACH under Bacillus atrophaeus. And this is good news because obviously these systems can make up 4 ACH, and some systems can easily produce 6 EAC, ACH equivalent or more, and this will satisfy the recommendations of ASHRAE 241P. We believe these are achievable goals based on this data. And I'll
Thank you very much for that. I suspect there will be a lot of interest in this. Just in the interest of time and for the other speakers, if you could grab Wally at the lunchtime, please, if you've got any questions. Thank you very much again, Wally.
thank you very much.